So, today is our final lecture on this course classical mechanics, and I will be doing one or two problems before we finally close this course. Our first problem is on this symmetric top, and top which children play with it. There is some thread, they wrap that thread on that top, and then there is a pointed iron nail, and then they throw it on the ground, and that it spins and it processes. So, that is the situation. A symmetric top of mass m is set spinning with an angular velocity omega s. So, that fast velocity, and its pointed end fixed on the ground. The distance of the center of mass from the pointed end is small l. The top precesses about vertical line through the pointed end with a constant angular velocity omega. So, when children play like that, it spins very fast, and then if it is at some angle to the vertical, then it precesses like this, keep spinning and then it precesses. So, that kind of situation is there. Find the conditions on these parameters, various parameters which are there in the problem, so that the top continues precession with this constant angular velocity at that theta. This is also known as steady precession. Okay, steady. This is also known as steady precession. So, here the situation, this is that top, symmetric top. Symmetric means you have this axis, and all directions perpendicular to the axis, they have same mass distribution. So, that is symmetric top, and then this is that pointed end on the ground. It is spinning fast, and then it is processing about this vertical line. This is going in a circular path, this whole top is going like this. So, that is the situation. You have to find the conditions on this mass, and then theta, this omega, capital omega, small omega, and other things, so that it continues precession with a constant angular velocity. So, what is our strategy? We first choose a principal axis system, and naturally this symmetry axis will be taken as the 3 axis E3. Then in this plane, this vertical plane containing this vertical line through the pointed end and this 3 axis. In this plane you draw perpendicular to this 3 axis, and that will be the 1 axis. So, this is our 3 axis. When it precesses, it goes somewhere else behind the board, let us say, then this comes out of the board, and perpendicular to these two will be our 2 axis. So, this will be 2 axis. Now, these are principal axis. Why? This 3 is a rotational symmetry axis, 3-fold, 4-fold, 5-fold, infinite fold, because the whole thing is symmetric. You rotate it by, it is a solid top. So, you rotate by any angle and you get the same mass distribution. So, this is a rotational symmetry axis, therefore, it has to be the principal axis, and this plane here, this plane is a reflection symmetry plane, and any line perpendicular to that has to be a principal axis. So, this is a principal axis, and if 2 of them are principal axis, then the third has to be. So, this is our principal axis system. Principal axis 1, 2, 3, but not fixed with the body, Okay. It is not fixed with the body in the sense that this is spinning. So, when this is spinning, these axes do not spin with that, right. Although this remains the same, but these 2 axes, they will not spin at that velocity with it. So, it is not fixed in the body. So, we will not use Euler's equations. Okay. Fine. So, this is our system, and then the angular velocity, and this is our origin, right, naturally this is our origin. So, angular velocity will be this omega, and then this is let us say z axis omega k cap, this is because of that precision, and then because of this is omega s and in E3 direction. And this k also you can write in E1, E2, E3. This is omega, this k vector will be cos theta times 3 vector, cos theta times E3 vector, and plus this is the unit vector k, cos theta in this direction and sin theta in this direction. So, sin theta times E1 cap, this is this thing k cap, and then plus omega s and E3 cap. So, you can write this as omega sin theta E1 cap plus omega s plus omega cos theta E3 cap. So, that is what this omega is, and you write what is L vector, angular momentum vector. It is I1 omega 1 E1 cap plus I2 omega 2 E2 cap and plus I3 omega 3 E3 cap. Since these are principal axes, therefore, I can write that, otherwise that 9 component matrix will be needed. Okay, so, this is it, and the torque tau, which is dl dt, that is our lap frame, this is equal to dl dt in the rotating frame 1 2 3 frame, and then 1 2 3 frame is rotating about that lap axis with omega, capital omega, and therefore, it is capital omega cross L. Okay. If this is the z axis, if I make an x axis and y axis fixed in the lap, then with respect to that lap frame, this 1 2 3 axis, they are just going around this vertical, which will be this omega. So, our frame is rotating at omega, and therefore, that omega comes here cross L. This is our lap frame or inertial frame. So, this is our relation, that is what we will be using. What is dl dt in 1 2 3 frame? Here is L, this is equal to I1. What is omega 1? Omega 1 is this. So, omega sin theta, and this is omega 1 E1 cap plus I2 into omega 2. What is omega 2? Omega 2 is 0. Omega 2 is 0, there is no omega 2 here, and so I do not have to write this. Then I3 omega 3, and what is omega 3? Omega 3 is this, and we will write that as omega 3. Let me keep it omega 3, where omega 3 is omega s and plus omega cos theta, capital omega cos theta. Okay. So, what is this dl dt? This dl dt is, this is constant, this is constant, this is constant. So, this component does not change with time, this is constant, this is constant. So, this component does not change with time. So, in this 1 2 3 frame, dl dt is 0, and so this is just, it is just omega cross L, and that means omega vector is here, this is omega vector, omega cos theta E3 cap and plus omega sin theta E1 cap. Okay. This omega is just omega in k cap direction, and omega in k cap direction we have already written omega cos theta E3 cap plus omega sin theta E1 cap cross with what? Cross with L, that is I1 capital omega sin theta, I1 capital omega sin theta, and then E1 cap and plus plus I3 omega 3, and that is in E3 cap. So, let us do this, with this omega cos theta I1 omega sin theta. So, it is I1, it is omega square, capital Omega square, then I have cos theta and sin theta. So, sin theta and cos theta, and then we have E3 cross E1, which is E2 cap. This is this term. Now, come with this. This is plus E1 cross E1 cross is 0, and therefore, it is this cross this. So, it is I3 omega 3 capital Omega sin theta, E1 cross E3 cap is minus E2 cap. So, it is minus here and E2 cap here. Okay. When you cross product with this term, E3 cap cross E3 E1 cap gives you E2 cap, E3 cap cross E3 cap is 0. When you cross with this term, E1 cap cross E1 cap is 0, and then E1 cap cross E3 cap gives you minus E2. So, it is in E2 direction. Okay. So, this is the torque, but from where this torque is coming? Where is the force? Torque of which force? So, if this top is the system, the forces are mg here, this is mg, and then some normal reaction and some friction perhaps. So, normal is this way and friction is this way, the total reaction is at some angle. But then our origin is here. So, this friction or this normal force will not have a torque about the origin. Remember, everything is about the origin, angular momentum about the origin, torque about the origin. So, these forces which are there from the ground, they do not produce any torque, the torque is produced from this mg only. And how much is that? If this is mg and this is the point, so and this angle is theta, so this angle is theta, so it is mg and then L sin theta, mg L sin theta. So, torque is equal to mg L sin theta, and you can see from this diagram, this torque is in this diagram it is clockwise from our side. I am finding clockwise, so it is away from me. So, it is minus E2 cap. Good, it is in E2 cap direction, and from here I am also getting E2 cap direction. So, compare these two, this is the same torque and the same torque here. So, you have I1, then omega square sin theta cos theta and minus I3 omega 3 omega sin theta is equal to mg L sin theta, and here it is minus mg L sin theta and E2 cap. So, this is equal to this. Now, sin theta you can cancel, sin theta here and sin theta here. So, that can be cancelled. What you have now is I1 cos theta capital Omega square and then minus I3 omega 3 and then capital Omega and plus mgl is equal to 0. This is equal to 0. So, from here you can try to write what this omega is, what this capital Omega is, and what this capital Omega will be. It is a quadratic equation. So, the first observation is that not all omegas are allowed. You need only real omegas. To get a real root of this quadratic equation, the discriminant should be positive or at best 0. So, that will put some restriction on this omega 3. So, let us see what it is. The discriminant is b square minus 4 AC, and I am working on this omega. So, this is our b, minus I 3 omega 3, that is our b. So, to get a real capital omega, I should have I 3 square and omega 3 square, b square, and minus 4 AC. So, minus 4 times, and this is I 1 cos theta, I 1 cos theta, and multiplied by that MGL. This should be greater than or equal to 0. So, omega 3 I 3 omega 3 square should be greater than or equal to 4 I 1 cos theta, 4 I 1 MGL and cos theta. So, I 3 omega 3 should be greater than square root of this, and therefore, omega 3 should be greater than or equal to 4 I 1 MGL cos theta, and then divided by this I 3, or you can write here I 3 square, like that. And remember, this omega 3 is omega s and plus omega cos theta, right. This was our omega 3. This capital omega is going to be small, we will just see. This omega s is to be fast enough to make this omega 3 greater than equal to this. So, this is the first condition for steady precision. Okay. And if the steady precision is there, we can find the value of this omega, capital omega, from this quadratic equation. So, omega will be equal to minus b, which is I 3 omega 3, and then plus minus the square root of this b square minus 4 AC, that is I 3 square omega 3 square, and minus 4 I 1 MGL cos theta, divided by 2a, that is 2 I 1 cos theta, and then omega, a minus b plus minus b square minus 4 AC divided by 2a. So, these are the two values of this capital omega. You can simplify it little bit. If you can take this I 3 omega 3 common out of it, 2 I 1 cos theta here, you get 1 plus or minus, then square root of 1 minus 4 I 1 mg L cos theta divided by I 3 square omega 3 square half power, right. So, I am taking this out, and when it comes out, it is I 3 omega 3, and that goes here. So, 1 plus minus, and then 1 here, and divided by 4 I 1 mgl cos theta divided by I 3 square and omega 3 square. Now, since omega 3 is large, to get a precision, omega 3 is large, and therefore, you can do a binomial expansion and keep only the first term. This whole thing is small. So, now it is equal to I 3 omega 3 divided by 2 I 1 cos theta. You know that 1 minus x or 1 plus x to the power n, when you expand, your first term is n x, and then you have more terms. So, if x is small, you can stop here. So, this half will come here, and I can do it here itself. So, this half comes here, and this becomes 2. So, if you take the positive value, it is 2 plus, and then this whole thing 2 I 1 mgl cos theta divided by I 3 square omega 3 square. So, this, and if you take the negative value, or so this, or I 3 omega 3 divided by I 1 cos theta and if you take the negative value, this negative value, so 1 minus 1 and plus this. So, it is just 2 I 1 mgl cos theta and divided by I 3 square omega 3 square. So, you have two values of this omega. Omega is this or it is this, and since this quantity is small and this 2 is sitting here, therefore, we can neglect this, and this number will be just this 2 cancels with this, and it is I 3 omega 3 and then divided by I 1 cos theta. This is one relation. This is one relation between those parameters. This capital omega is equal to I 3 omega 3 I 1 and then this cos theta. So, this I 1 is the moment of inertia of this top. Okay, I have to erase the top. So, if this is the top and this was 3 axis, this was vertical and this is 1 axis. So, I 1 is moment of inertia if this of this torque about this line. So, be careful about this line, this is I 1, and I 3 is the moment of inertia on the top about this line I 3. So, you put those things and you get here. The other choice is this, and then this choice you have I 1 cancels out, this cos theta cancels out, and then I 3 omega 3 will cancel one power of this. So, what you have is now mgl only in the numerator, mgl in the numerator and divided by I 3 omega 3. So, this is another possible relation. So, either omega is equal to this or omega is equal to this. You have to start the motion in this particular fashion, that this is the relation between them or this is the relation between them, then it will continue to process with uniform angular velocity. This is known as slow precession, and this is known as fast precession. Both are possible depending on how you start, but you have to either start this way or start that way. In general, in practice, this is the way the tops are started, with large omega 3 and small precession velocity. So, the question is, a thin hoop of mass m, hoop means you have a mass which is on the periphery, it is a kind of a ring, and the mass is at the periphery only, although there will be spokes from the center, but those things will be treated as light. So, a thin hoop of mass capital M and radius r is fixed to a rod of length capital R as shown in the figure. So, the radius here is capital R, the radius here is capital R, this is capital R, and this rod is also having the length capital R as shown in the figure. The hoop rests on the ground. So, it rests on the ground and in a vertical plane. So, you have a hoop here, suppose you have a hoop here and it is placed on the ground and the hoop is vertical, okay. And then this rod is there, from the center you have a rod, and the other end of the rod is attached to a vertical rod through a bracket that can rotate freely. So, here is that vertical rod, here is the bracket, and the other end of this rod is attached to this bracket, and this rod can rotate here in this bracket. This whole bracket can rotate, and therefore, this whole thing can rotate about this line. The hoop rolls on the ground without slipping. So, it rolls on the ground and without slipping here. So, if you have a hoop here, rod here attached to this vertical rod, and then this hoop is rolling. So, it is rolling, but as it rolls it cannot go straight because of this rod here, and the rod can rotate here. So, this whole hoop will go like this while rolling. So, that is the situation. The hoop rolls on the ground without slipping, the center of mass thus rotating about the vertical rod, thus rotates about the vertical rod. Let this angular velocity be omega. So, this is omega, this center of mass goes in a circular path about this line. with this angular velocity. Now, the question, find A, the angular velocity of the hoop. This hoop as a whole, what is the angular velocity? It is spinning, at the same time it is rotating, and then the angular momentum of the hoop about the position of the bracket. So, this is the point at which we need angular momentum. So, these are the two questions. So, let us take this point as A, this point of B. I can directly write omega, not a big problem. Because of this I can write the velocity, angular velocity. Because of this I can write the angular velocity, then no slipping condition I can put. But let us see one more small technique that you can use in other problems also. So, we have to find the omega, small omega, the angular velocity of this hoop. Now, for any object which is rotating, velocity can be written as omega cross r. Velocity of any particle is velocity, general relation is v equal to some point, you pick up some point and then r of that point with respect to this. So, velocity of say point q is r of this q with respect to p, that is the general one. But if you pick up the right point, and here we are picking the right point which is 0, this point is 0, this will be our system, hoop plus that horizontal rod. We will consider this as the system, and this will be our reference point, which is at rest, and therefore, we have this just v equal to omega cross r if I use this point as the reference. Now, for point B, it is rolling without slipping. So, v of B should be equal to, according to this, omega cross r of this point B, this, and that is equal to omega cross AB vector, and this is equal to omega cross, and this is 0, okay, this is 0, because at point B there is no velocity, it is rolling without slipping. So, this is 0, and therefore, this omega must be parallel to AB. The cross product is 0, therefore, it has to be parallel to AB, and therefore, I can write omega as some k. And what is AB vector? What is this AB vector? This AB vector is this AC vector and plus CB vector. So, this is AC vector and CB vector. Now, let me take axis. This will be our 3 axis as usual, symmetry axis we take as 3 axis. Then this vertical will be our 1 axis, this will be 1 axis, this will be 1 axis, and then the perpendicular will be 2 axis like this. So, 1, 2, 3 origin here. This is principal axis system. This 3 is a principal axis, rotational symmetry axis. Then this is a reflection plane, this is a reflection plane, this side and this side they can reflect on each other, and perpendicular to that will be symmetry will be principal axis. So, this is principal axis, this is principal axis, and therefore, this is principal axis. So, in this principal axis system, let me write this is K, and AC is R E3 cap, plus CB is R and then minus E1 cap. So, R and minus E1 cap. So, I can put minus here and E1 cap here. So, that is omega. Omega is K R E3 cap and minus R E1 cap. Now, once this K is unknown yet. Now, once I have written the expression for omega, with this omega I can also write the velocity of this point C. So, what is the velocity of point C? Velocity of point C is equal to omega cross position vector of C, and omega is K times R, you can write here, and E3 cap and minus E1 cap, this is omega, and cross R of C, position vector of C, which is R E3 cap, and that you can write now kr square E3 cap is 0 and minus E1 cap cross E3 cap will be E2 cap. Kr square 0 here and E1 cap cross E3 cap is minus E2 cap, and therefore with this minus it is positive. So, it is this. But then we also know that this center is going on this circle with this omega, and therefore the speed is omega times r. It is just going on a circle with a constant angular velocity capital omega, and therefore the velocity, linear velocity will be this capital omega into r. And what will be the direction in terms of our axis system? Since it is going that way, so it has to roll, and if I am looking from this side clockwise, and therefore it is on the other side, so minus E2 cap. So, Vc is also equal to omega r in minus E2 cap direction. Okay, that we know from the rolling. If it is rolling this way, the particle this is going in this direction this way, and therefore we can write the speed of this. The speed of this will be in minus E2 cap direction, in that direction, and 2 is in this direction. So, it is this. Now, you can compare these two Vc's. I got it in two different ways, but the same velocity v, and therefore this k r square E2 cap, or E2 cap you can leave from here, k r square is equal to minus omega r, and so k is equal to minus omega and by r, and hence omega is equal to, come from here, omega is equal to k. K is minus capital omega by r. So, it is capital r will cancel. So, capital omega here and minus is there. So, E1 cap minus E3 cap. So, that is the answer of the first part. So, this is all answer of the first part. Find the angular velocity of the hoop. So, that is the angular velocity of the hoop. The angular momentum of the hoop about the position of the bracket. So, I need angular momentum here. So, you know what it is? Angular momentum is I1 omega 1 E1 cap plus I2 omega 2 E2 cap plus I3 omega 3 E3 cap. You have to make sure that your axes are principal axis system, then only you can write this, otherwise that 9 components matrix will come. So, this is L. In our case it is I1. So, if it is a hoop, whole mass is concentrated on the periphery and the radius is capital R, mass is m, and therefore I1, what is I1? I1 is moment of inertia of this with respect to one axis, and the axis is here, this is one axis. So, about this diameter the moment of inertia will be m r square by 2. Okay, it is a hoop ring. So, about this diameter it is this, then parallel axis theorem to get the moment of inertia about this, and that will be I1 will be mr square plus mr square by 2 and omega 1. What is omega 1? This is omega. So, omega 1 is this capital omega. So, capital omega and then this E1 cap, right. I1 is here, omega 1 is here, and E1 cap is here. Omega 2, I do not have any omega 2, there is no 2 component of omega. So, this term I need not write, and then this term I3. What is I3? Moment of inertia about 3 axis, and that is the axis of the hoop, and so it is mr square, it is mr square. Omega 3, what is omega 3? Omega 3 is minus capital omega. So, minus capital omega and E3 cap, that is it, that is it. 3 by 2 mr square omega E1 cap minus mr square omega and E3 cap. So, that is the angular momentum. Now, you can go further to write if there is a torque, if this L is changing with time, and if there is a torque, from where the torque is coming, what are the forces which are creating that torque, and so on and so forth. What is the force that is taking the center of mass in the circle, and all those things you can further do exercises with this situation. Okay, so with that I close this classical mechanics course. Had been a good experience, revised many things that I used to teach at IIT Kanpur a few years ago, and learnt many things. I hope you also enjoyed it. So keep enjoying physics. Thank you very much.